So start this up. Okay. So you've got your test back. I wouldn't say it was a great test. There was a lot going on, right? And so, but I will say, oh, weird, different. We always had these chairs in here. Doesn't matter. So, I will say this though, as long as you do better on the final, right? I'll pretend this one didn't happen. I'll just put the weight on the final, right? But I won't know that until you've written the final, right? And so just kind of, if this was a bad test, then if you feel like you can do better on the final exam, great, right? Then don't worry about this test, because I do feel like if you've got a bad test, it kind of puts you off your game a little bit, right? And so I don't want you worrying about that. I just want you to kind of say, okay, I'm going to learn from this, because all of those things that we did there will come back up on the final, right? So just those are yours to keep. And I didn't make solutions because I just did mine really sloppy and kind of very quick. And so, but you do have the solutions, right? Because they're just from that huge solutions book. So you can just match them, and you've got the solutions. And so they're in there for that practice document, the solutions that I posted. Okay, so you've got the solutions, and I didn't bring it with me, but I can tell you which questions are which, maybe next day or something, right? Post it. Okay, so test 1, done. Handouts for chapter 3. So this week we're going to work through chapter 3. There's quite a bit in here, especially in the beginning, that we're not really going to need for the final. So what I want to do is I want to just kind of give you the handouts, right? But the stuff that we focus on will be the stuff that we need to do, right? And so, of course, looks all innocent. 3.1, one little page. All about 2 pages or so. But there's a lot in there. I don't know what I'm sitting on here. Anyways, it doesn't matter. All right. Any questions though before we start? No. All right. So 3.1 is on quadratic functions and models. And you've got it there, right? But in general, a quadratic function is if we have something like f of x equals ax squared plus bx plus c, right? As long as a is not equal to 0, right? Because then that term would go away and then we don't have that x squared term in there. So we have to have some sort of a so that we have an x squared term. So we've seen quadratic functions before, right? We've got the quadratic formula that tells us how to solve for the X-intercepts, right? So we have used the quadratic formula before. The quadratic formula to solve for the X-intercepts. Oops. 1 week off and my writing just went out the window. Can imagine what it was like yesterday. There. Not that it was very good to start with. Right where we have x is equal to, what is it, negative b plus minus the square root of b squared minus 4ac over 2a. Hopefully. Good. Right, so that's how we would solve for the x-intercepts, right? And so we've seen the quadratic formula, we've seen a quadratic equation, and so today we're just going to talk a little bit more about it, but also to be able to manipulate it to find where the vertex is. So a quadratic equation, a quadratic equation will have the shape of a parabola, right? Because it starts with that x squared term, and so it's going to have this kind of parabolic shape. We'll have the shape of a parabola. And so if a is greater than 0, right? So if a is positive, remember a is that leading term, the leading coefficient on x squared. And so if a is positive, then we've got this upward facing parabola. So then we've got something like this. Oh, that wasn't very beautiful, but that's okay. Right. And if a is less than 0, remember a can't be 0 because then the x squared would go away. So then we've got this kind of downward facing thing. Flip it on its across the x-axis. These points here, this is what we call the vertex, right? The very bottom or the very top. We could also call this a maximum and a minimum, right? In this case, if a is positive, then that vertex is a minimum. And if a is negative, right, then that vertex is at the very top, making it a maximum. Okay. Now the tricky part is going to be to try to find what the value of that vertex is, right? And so what we can do is we can use this fact, but it's a little bit trickier than it seems. Well, it's a big box. It's that second box that you've got on your handout. Oh. But I'll just bring it in here so we can look at it. So here, if we've got a quadratic function in the form ax squared plus bx plus c, if that's the form that we're used to seeing it in, right? Then we can re-express it in the form f of x equals a times x minus h squared plus k. That's weird, right? But what we call this the standard form. So the standard form is f of x equals, a times x minus h squared plus k. I usually write my k's kind of cursive like this because otherwise my h and my k end up looking the same, right? So that's why I've got this kind of cursive k. Thanks. All right. So how are we supposed to get from ax squared plus bx plus c to this? Okay. It does say by completing the square. And I have this sneaking suspicion that that was one of the things that I said, hey, let's leave it until we need it. Now we need it. Here we go. It's actually, I'm going to pull it in. It's in your 1.5 notes. So that was a while ago. We didn't need it until now. It's on the second page, I guess, here. But I'm going to bring it into our notes. Oh, I copied a lot there. How about, I'll make little notes here before I do. To get from f of x equals ax squared plus bx plus c to f of x equals a times x minus h squared plus k, we need to complete the square. And so here, this little note here is from section 1.5, from 1.5 notes. Okay. The key part here is, of course, going to be this guy, which I'm going to zoom in on now. Yeah. So as long as we're able to isolate x squared plus bx, then completing the square says that as long as you're able to add whatever b is in this case over 2 squared, right, then we're going to be able to write it as, okay, so this little guy we can rewrite as x plus just b over 2 all squared. Okay? So that's how we complete the square. The problem is that we can't just add this willy-nilly, right? We have to add and subtract it. Right? And so what I want to do is I want to do it in general. Okay, so using just the ax, bx, whatever. And then we'll do a couple with numbers, and it'll be better. So those are the facts that we're going to use. So if we start with f of x equals ax squared plus bx plus c, right? Completing the square says that as long as you're able to have x squared plus bx, you can complete the square there, right? And having an eye on where we want to go, we want to end up at a times x minus h squared. Okay? So what we're going to do is I'm going to kind of pull this guy to the side. So put kind of imaginary, kind of pull it to the side. It's still going to be there, right? But it's going to be part of that k that I have at the end of my standard form. Yeah? And so what I'm going to do is I'm going to kind of treat these, I guess I can do real. They're not actual brackets, right? They're just kind of mind brackets. Complete says just x. And so what I'm going to do is I'm going to divide by square, but also for b, right? It just leaves what I do is a on the out x plus divided by a, I multiply it back in a plus b, and then plus c. gets a little bit. What happened now, this is what I want to complete the square of, right? Because I want to rewrite it ultimately as x minus h all squared, right? And so I want to complete this square. And what I want to do is I want to make sure that I keep b over a as if it's the b. That's what gets confusing because we already have a b, but now it's a new b, right? And so you can replace it with d if you want, right? But I'm going to keep it as b over a just to show you. And so here I'll make a note that now we can complete the square. And I'll add another note, right? By adding, remember that we have to add b over 2 all squared, but our b is actually b over a, right? Because it's whatever's on the x. And so for us, right, by adding what would it look like? B over a over 2, just kind of emphasizing that that's one thing, all squared. Okay. If I'm adding it inside, I have to subtract it somewhere else, right? And so what I'm going to do here is I'm going to say, okay, well, that means I've got a times x squared plus b over ax plus b over a over 2 all squared. And then if I'm adding it, right, I have to remember that I also need to subtract that. Right? So what I'm going to do is I'm going to go minus b over a over 2 all squared. And then don't forget that plus c. I only want this portion here, right? This is my square, because this I can rewrite as x plus b over a over 2 all squared, right? So I want to pull this outside and put it outside with the c. But to do that, I have to multiply it by a, right? Because a is multiplying all of this, but I'm allowed to do that as long as I bring this a in here, then I can push it outside. Okay? So here, this becomes x plus b over a over 2 squared, oh, sorry, all squared. So what I'm going to do is multiply that a inside. So I've got a times x squared, or actually, I already showed you that it equaled x. Maybe I'll keep it steady just to show. X squared plus b over ax plus b over a over 2 squared. If you went straight to x plus b over a over 2 all squared, that's fine too. But what I want to do is put a bracket around that and then minus a times b over a over 2 squared plus c. So now I've got a times x plus b over a over 2, make that bracket bigger, all squared. And then minus a times b over a over 2 squared plus c. B over a over 2, you can rewrite. And if you've already done it, then that's fine. Totally good. B over a over 2, technically over 1, right? I've got a fraction over a fraction, so I can rewrite that, right? I can flip and multiply, so that becomes b over 2a. So now what I can write is I've got a times x plus b over 2a squared minus a times b over 2a squared plus c. Right, doing the same thing with the b over a over 2. And I can simplify a little bit, right, by bringing the square inside the b over 2a. So I get a times x plus b over 2a squared minus a times b squared over 2 squared, which is 4 times a squared plus c. Now I see that I can cancel one of these a's. And so I get a times x plus b over 2a squared minus b squared over 4a plus c. Now I'm going to recall we want this in the form f of x equals a times x minus h squared plus k. So rewriting this a little bit, right? Especially paying attention to that I want a minus here, right? And I have a plus in here, so I can rewrite, I can split that plus as minus a negative number, right? And then what I'm gonna do is, just to make it a little bit cleaner, this whole term is k, right? But if I just write plus c minus this, then c minus b squared over 4a is going to be our k. So we can write that a times, and I'll do bigger brackets here, times x minus negative b over 2a squared. And then plus c minus b squared over 4a. So now I can say that, okay, well, this term here is my h, and this term here is my k. Oops. K's aren't behaving. There. Wow, that's weird, right? It's a lot to start with. it'll be better when we have numbers, right? But this is what we're doing in the end, right? And so why would we want to do this? Remember we said that the whole goal was to find the vertex? Well, what the rest of that box says that we brought over is that, okay, if we're able to rewrite it in standard form, then the vertex is going to be at HK. So all of a sudden, it's really easy to find the vertex as long as we're able to rewrite it in standard form. Right? Not so easy if we have it just in, I don't know, general form, I think it's called, ax squared plus bx plus c. But if we have it in standard form, then we can find the vertex because that vertex is going to be at HK, right? The x value will be h and the y value will be k. So, once f of x is in standard form, we can easily find the vertex because it will be the point HK. And then just kind of as a side note, right, where h is going to be negative b over 2a, and k is going to be c minus b squared over 4a. That's not something that I want you to remember or anything, right? I'm just linking it to the previous, what we just did, right? So the vertex is at HK. Okay, all right. How about we do an example? We'll start, how about we start kind of nice and slow. Which one do we want to do? Let's do 10 first. Just nice and slow. We'll do this one together, and then I'll let you guys do probably 22 on your own. Kind of pre-baked some of these just to make sure. Yeah. So if we have f of x is x squared plus 4x minus 1, right? So now we've got x squared plus 4x minus 1. And so the question asks us to express it in standard form, right? But then from there, find the vertex, and then the x and the y-intercepts. Remember, you can find the x-intercepts using the quadratic formula. Right? And then the y-intercept is just where x is 0. And then we're going to sketch the graph sort of, right, just quickly. And then using the graph, we'll be able to find the domain and range. So what I want to do here, right, is I want to write this in standard form. Now, there's no a that I have to pull out front, so now I can just focus on x squared plus 4x and then minus 1. So So we want to complete the square here, right? Our b in this case, right? Remember, to complete the square, we add b over 2 all squared. Right? B in this case is 4. Right? And so we have this equals x squared plus 4x plus 4 over 2 squared. Oh. And if I'm adding it, I have to subtract it as well because I can't actually change this equation, right? So minus 4 over 2 squared. And then on the outside, not really, I have minus 1. So a little bit nicer when you have numbers, right? 4 over 2, well, that's just going to be 2. And so we've got x squared plus 4x plus, but what I'm going to do is I'm going to leave it as just 2 squared. And then I'm going to bump that minus 2 squared outside, right? Because there's no multiplier. So the brackets there aren't actually doing anything. So I can put it outside the brackets and minus 2 squared minus 1. Because by completing the square, this becomes the same as x plus 2 squared, which you can check, right? X plus 2 squared is x squared plus 2x plus 2x, that's 4x, plus 2 times 2, that's 2 squared. Right? So now we've completed this square. And we've got x plus 2 squared minus 4 minus 1 minus 5. So this is in standard form. A times x minus h squared plus k. A in this case is 1, right? So A is 1. That being positive tells me I've got this upward facing parabola, right? And then x plus 2, I have to kind of rework into x minus h. We use that same trick, right, where we write that as x minus negative 2, right? And so h is negative 2 and k is negative 5, right? Because it's plus k, but we've got minus 5, so we must be at negative 5. Therefore, the vertex, which is at HK, is going to be at negative 2, negative 5. Oh. Cool. So we expressed it in standard form, which meant that even though expressing it in standard form is quite a bit of work, now finding the vertex is a lot easier, right? And so now we have the vertex, we have it in standard form. We also have to find the x and the y-intercepts, right? And so you can use the quadratic formula if you want, or you can set it equal to 0. Either way, the quadratic formula might be a little bit easier, right? Just because we're familiar with it. So let's say we want to find the x-intercepts use quadratic formula. So we've got x is negative b plus minus the square root of b squared minus 4ac over 2a. This is going back to that original form, right? Ax squared plus bx plus c. And so now, let's write down what it was. X squared plus 4x minus 1. F of x is x squared plus 4x minus 1, just so I have it. My a is 1, my b is 4, and my c is negative 1. So now I've got negative 4 plus minus the square root of 4 squared minus 4 times 1 times negative 1 over 2 times 1. Negative 4 plus minus the square root of 16 plus 4, 20. Over 2. I'm going to get, well, the root of 20. 20 I can rewrite as the square root, 4 times 5. The square root of 4 times 5. Just to show you what's going on. But most calculators will just be able to give you the exact form. I know this one just defaults to the exact form, right? And so, which is the square root of 4 times the square root of 5 over 2. Negative 4 plus minus 2 root 5 over 2 puts me at negative 4 divided by 2, because I can divide 2 on both sides. And so negative 2 plus minus root 5. So I get negative 2 plus, actually I'll do minus first, minus root 5. Oh. Negative 2 minus root 5 and negative 2 plus root 5. So then I get roughly, because that's going to be hard to put on the number line, right? And so we use the decimal approximations. And so roughly negative 4.236 and negative 2 plus root 5, bless you, is at positive 0.236. So that means that it's going to cross. So these are the X-intercepts, right? Which is when y is 0. Oh, it came from here. So I rewrote 20 as 4 times 5, because then I'm able to put the square root, as long as I'm multiplying in here, I'm able to distribute the square root and then I can cancel. But if we went from here on your calculator, you could have gone straight from here down to here. I just wanted to show where it came from. And hopefully when I do that from the get-go here, negative 4 minus the root of 20 divided by 2, phew, I get to the same thing. So I showed a few extra steps, but it was fun, I guess. So, like I said, you could go straight from here to there. using your calculator. So we've got our x-intercept. We need our y-intercept. The y-intercept is when x is 0, right? And so the y-intercept is when x is 0. You've got two options for f of x, right? You can use the original x squared plus 4x minus 1, which is probably my preferred one just for plugging in x equals 0. You're going to get the same thing if we've found the proper standard form, right? So plugging in x equals 0 into here, right, puts me at 2. So 0 plus 2 squared. So 4 minus 5. So that puts me at -1. Putting in x equals 0 here, I get 0 plus 0 minus 1. Either way, I should end up at -1, right? Because they're the same formula. And so we can use either f of 0 equals 0 squared. Oh shoot, where was it? Plus 4 times 0 minus 1 equals -1. Or f of 0 as 0 plus 2 squared minus 5, which is 4 minus 5, which is -1, right? Either way, the y-intercept is at 0, -1. So we found all the points that we had to. We're just going to sketch the graph, but then, of course, because we have Desmos, we're just going to double check that we got the same thing. Right? So, okay, what did we say? It's kind of rough sketch here. So the y-intercept is at 0, -1. And so I'll put it, I don't know, somewhere here. 0, -1. I also have the x-intercept is when y is 0, so I'm at -4.236 and 0.236. So -0.4, or sorry, not 0.4, 4.326 and 0. And let's say 0.2360, right? That one was positive, I think. Yeah. And we also have the vertex. The vertex is the very bottom of it because A is positive, right? So we know it's pointing upwards, and it's at -2, -5. -2, -5, let's put it somewhere down here. Right? We're just making quick sketches. It's not going to look very good, is it? I think I have to move, oh, whoops. Move this point over a little bit to make it sort of look a little bit better. Oop. Cheating. So then my sketch, well, let's do it in green here. I know it's going to have this parabolic shape. And so I can start down here at the vertex and just kind of send it up this way and start down here. And that's the sketch of my graph. We can check this in Desmos by saying, okay, we've got, what was it? I'm just going to use the x squared plus 4x minus 1. I think I prefer to use the one that was given to me so that I can really check that I did everything right, right? And so if we click on here, first of all, the vertex seems to be at -2, -5. The y-intercept is at 0, -1. So far, so good. Hey, it looks pretty good. Right, so we're able to check that we did all of these right. Of course, in the test, you won't have that, right? But when you're practicing and you want to check your work, then you can just go to Desmos and make sure that you got it right. Let's do a trickier one. How about 22? So I want to give you guys a little bit of time to work on it, especially finding that standard form, because that's the tricky part, right? 22 is f of x equals 2x squared plus 12x plus 10. Remember that you first have to pull out that 2, right, from the x squared.
we reached here.
Mm-hmm.
This is k. We can solve this k
Mm-hmm.
by squaring 3
Yeah.
by 2.
Yeah.
And then subtract the value from the 5.
That's right.
And that will be our k.
That's right.
And this, if it is positive, then we will write h is equals to negative 3 by 2.
Yeah.
And a is equals to 2.
Mm-hmm.
Thank you.
Should we get started? We'll start nice and from the beginning. So here, first thing we want to do, right, is we want to pull out that 2, right? And so we've got this 2 times x squared plus, and then 12 divided by 2 makes 6x. And then I'm going to put brackets around that and just leave the 10 alone. I guess I probably could pull in the 10, but just so that I'm always using the same method, I'm gonna just pull it to the side. Right? I'm sure you could pull it in and then complete the square with the 5, but just to use the same method, I'm just gonna put the 10 to the side. So now I have 2 times x squared plus, so now my b in completing the square is 6. So 6x plus 6 over 2 squared. Oop, and then I have to subtract it. I almost forgot to subtract it. Minus 6 over 2 squared. And then plus 10 on the outside. So now I get, well, remember how we had to pull that 2 inside and then push it out to the 10? So what I'm going to do is I'm going to leave 2 times x squared plus 6x times 6 over 2 squared, but then minus 2 times 6 over 2 squared plus 10. This becomes 2 times x plus 6 over 2 minus 2 times, I guess I could rewrite 6 over 2, but I just want to show that that's the 6 over 2. So 2 times 6 over 2 squared. I'll bring that square in actually. 6 squared over 2 squared plus 10. Oh, and then I've got a square on the outside, x plus 6 over 2, and then I forgot that square on the outside. That was the whole point of completing the square. So this becomes 2 times x plus 3 squared minus, and then this 2 times 6 squared over 2 squared, well, I mean, you can use your calculator. 6 squared is 36 divided by 4 is 9 times 2, oops, puts me at 18, so negative 18 plus 10. Which is, so now we've got 2 times x plus 3 squared minus 8. We can check check that this is actually the same, right? By expanding the x plus 3 squared and then making sure that we end up back in the original form that we started with, right? And so check that 2 times x plus 3 squared minus 8, does it equal what we started with, 2x squared plus 12x plus 10? Right? It should, they should be the same. So what we'll do is we'll manipulate the left-hand side until it ends up looking like the right-hand side, just to check, right? This isn't something that you need to do, but it's just a nice way to make sure you did it right. So 2 times x plus 3 times x plus 3 minus 8. I'll just leave that right-hand side. I don't need to write it out every time because it hasn't changed. 2 times x squared plus 3x plus 3x plus 9 minus 8. Bring that 2 in, but also consolidate the 3x plus 3x in the same move. So I get 2x squared plus 3x is 6x times 2. So 12x plus 18 minus 8, which it does equal 2x squared plus 12x plus 10. Woohoo! All right, just to check. All right, back in the real world here. So we know that this standard form is good. So now we can say, okay, well, here, paying attention to the x plus 3, right? Standard form has x minus h, so you need to make sure that it's negative 3. And so we've got, so in f of x equals 2 times x plus 3 squared minus 8, h is negative 3 and k is negative 8. So therefore the vertex, which is at hk, is going to be at negative 3, negative 8. I also know, right, that since this 2, right, my a in standard form is positive, so that means it's going to be pointing upwards, right? And so since a is 2 is greater than 0, right, I have this kind of a shape, right? And so here I am at negative 3, negative 8, just to get a general idea of what it's going to look like. This is also what we call the minimum, right? And so you'll see further down on the page, it talks about maximum and minimum values, but that's what we're doing already, right? So we're not going to spend too much time on this, but since a is 2 and it's greater than 0, negative 3, negative 8 is the minimum. That's just kind of a side note to tie into the rest of the notes that you have. Right. It doesn't look like an X. There. So now we have the vertex. We want to find the X-intercept and the Y-intercept. I saved the Y-intercept for last because it's the easiest. Right. And so the X-intercepts we find at x equals negative b plus minus the square root of b squared minus 4ac over 2a. Yeah.
Can you also find them by taking the square? X-intercepts?
Yes, in fact, you could go and set the standard form equal to 0, right? Just remember when you, so then you have 0 equals 2 times x plus 3 squared minus 8. So then you could slowly pick, you know, you get 8 over to the left-hand side and then divide by 2, then you're at 4. and then you're at x plus 3 squared. Remembering when you take that square root, it becomes plus minus the square root of 4. So it becomes plus minus 2, just like in the quadratic formula. So you could do that as well. Can you complete the square? Are you going from this standard form or the original?
From the original.
The original?
No, I guess you would have to.
I think you would just end up here anyways. This makes it easier to solve for though, right? If you're solving for it that way. But because we've got the quadratic formula, I mean, just gonna go right for it. So remembering that f of x, the original form was 2x squared plus 12x plus 10. So b is 12, so negative 12 plus minus, whee, what happened there? Square root of 12 squared minus 4 times 2 times 10 over 2 times 2. So I'm at 12 squared. I'm working under the square root for a little bit. 144 minus 4 times 2 times 10 in brackets. 64. Let's hope the square root of 64 becomes 8 over 4. Skipping some work there, but I've showed it all, and so I'm allowed to do that. So I've got negative 12 plus, or sorry, I'll start with minus 8 because I like to have the left-hand side first. Minus 8 divided by 4. Negative 12, oh, I did it again. Minus 8 over 4. And negative 12 plus 8 over 4. First one's at negative 5. And negative 12 plus 8 over 4, negative 1. So finally, the y-intercept is when x is 0. Right? And like I said before, you can either use the standard form or the general form, right, which is the original form. Doesn't really matter. I'll just use the original one because that's the one I have here, right? But it really doesn't matter. F of 0 is 2 times 0 squared plus 12 times 0 plus 10. Positive 10. If I have to sketch this out without any grids or anything, just a rough idea. Looks like I'll start with my y-intercept because it's the closest here. I'll put it somewhere up here at 0, 10. I cross the x-axis at negative 1, negative 5. And so let's put that here, negative 1, 0. And maybe here, negative 5, 0. Really rough because, I mean, I didn't put any grid lines on here. And then finally, my vertex, which is the first thing I found, is at negative 3, negative 8. Maybe somewhere around, I don't know, there-ish. It's going to look a little wonky. Yeah. Maybe I'll have to start Whee. That's all right. It's hard when you have to hit 2 and you didn't spend very much time on the axis. We can check it in Desmos, right? And so we've got 2x squared plus 12, oops, plus 12x plus 10. Down here, -3, -8, that's great. -5, 0, -1, 0, so far so good. And up here, 0, 10, phew. Okay. So, any questions about those ones? Okay, I wanted to do another one of these, but I'm looking at the time here. I think we'll move on. I wanted to do 24 too. Let's just do 24 together. I know. (24) because the rest of the problems in section 3.1 just use the same tools, and those very last few questions, 47 and 48, I'd label those as optional, right? Because then you're working backwards. I give you the vertex and a point that it flows through, right? And then you can work your way backwards, but we're not going to do that. So you can label that as completely optional. But the other ones you can do no problem, right? The hard part is finding the standard form and then going from there. In fact, how about we just find the standard form, right? Everything else is probably, hopefully okay, right? X-intercepts, Y-intercepts. It's just finding that standard form, and the vertex, well, once you have the standard form, even the vertex is easy. Find the standard form of f of x equals 3x squared plus 2x minus 2. Okay. If f of x is 3x squared plus 2x minus 2, first thing I'm going to do, right, is I'm going to pull that minus 2 over to the side, right? Same procedure as we've been using, right? I'm not going to bother seeing if I can incorporate it. I'm just going to pull it to the side. And so I have to pull out that 3 in front of the x squared. So I get 3 times x squared plus 2 over 3x minus 2. Right? So this is looking a lot more like that, the proof that we did in the beginning, where we just used the letters. Right? Now we've got b over a. But now, in completing the square, the b that we're dealing with is 2 over 3. Right? And so to complete the square, right, we've got 3 times x squared plus 2 over 3x plus 2 over 3 over 2 squared minus the same thing, right, because I'm technically adding 0, minus 2 over 3 over 2 squared, and then minus 2 on the outside. Just as a reminder, right, 2 over 3 over 2, I can rewrite as 2 over 3 over 2 over 1. 2 over 3 over 2 over 1, flip and multiply. And so this becomes 2 over 3 times 1 over 2 Yep. Becomes 1 over 3. Right. So now I've got 3 times x squared plus 2 over 3x plus 1 over 3 squared minus 1 over 3 squared minus 2. A little bit nastier with those fractions. Got 3 out front still, times x squared, and what I'll do is I'll make this bracket a little bit bigger. X squared plus 2 over 3x plus 1 over 3 squared, right? Block that off because that's my essentially x minus h squared minus, and then remember I have to bring that 3 onto the minus 1 over 3 squared, right? Because to bring it outside. So minus 3 times 1 over 3 squared and then minus 2. Because this section I can now rewrite as x plus 1 over 3 all squared. So this becomes 3 times x plus 1 over 3 squared. And then minus 3 times, and I'll bring the square in, 1 squared over 3 squared minus 2. Three times x plus 1 over 3 squared minus, and then so I've got 1 squared over 3 squared times 3, right? One of these guys is going to cancel. So I get minus 1 over 3 minus 2. If I want to do it properly, right, you could use your calculator, that's fine, right? But if I wanted to do minus 1 over 3 minus 2, I would have to multiply the 2 by 3 over 3, right, to get that common denominator. And so I'm going to show that here, times 3 over 3. So now I'm at 3 times x plus 1 over 3 squared minus 1 over 3 minus 6 over 3. So now I'm at 3 times x plus 1 over 3 squared minus 1 minus 6 over 3. So negative 7 over 3. So I get 3 times x plus 1 over 3 squared minus 7 over 3. So here, right, in terms of h's and k's, right, if I have a times x minus h squared plus k, then a is going to be 3, h is going to be negative 1 over 3, and k is going to be negative 7 over 3. Oops. And then from here, you're on easy street in comparison, right? By comparison, I guess it is. Is it? Anyways. Okay. So I'll I'll leave the rest to you, right? Because you can check your work on Desmos, make sure that you're getting the right things. But that's the hard part, right? Finding the standard form. So the rest of 3.1, right? Use the same thing, find it in standard form, just saying that, hey, the vertex, depending on if it's opening up or opening down, is going to be either a maximum or a minimum, right? And that's all it's saying. Section 3.2, we're only going to kind of touch base in really quickly because we're going to spend more time graphing. So what we did with the parabola, that's good, right? We could go ahead and do the same thing with any polynomial, right? But as long as we've got it under control for the quadratic, then we're good. So 3.2 is polynomial functions and their graphs. So there's a lot of these notes that I'll just leave for you because we're not going through them. I wouldn't worry about them too much, right? But just try them and see how it goes. But in general, the main takeaway here is, and I really can't remember, 3.2. If we talked about I feel like we talked about the terminology for polynomials, but you'll correct me if we didn't. Did we talk about, or was that in my calculus class? Anyways, it's confusing when you do pre-calc and calculus in the same term. What have we done? So a polynomial, right? And I know we have talked briefly about polynomials, right? It's going to be something of the form. So we've got a coefficient, right? And then x to the power of n, where n is the highest degree, right? Highest power. And so we call this degree n, right? And so usually when we're working with polynomials, we write them in decreasing powers of x. Right? So we just kind of rewrite it decreasing powers of x because all these a's in front, we've already kind of used the term coefficients, especially in the quadratic equation, right? Ax squared plus bx plus c, right? A and b and c are all coefficients. And so we've got these coefficients in front of all the x's, and then the little constant, right, c in our case, if we're referring back to the quadratic, is going to be the constant term or the constant coefficient, and whatever is the coefficient of the highest power, that's going to be our leading coefficient, and then this whole a n x n is going to be the leading term. Where one important thing that I'll say is that this is a term. This is a term. This is a term. And even this is a term. So I'll add that terminology on, haha, pun intended, terminology. On there. Because it's using the word term, but it's not really defining it. Okay. So that's just to be able to talk about polynomials in general, right? And so what we have is kind of a cool feature that, and I just feel like we've talked about it before, but we can talk about the end behavior of any polynomial, which is kind of cool. So to understand the general kind of shape of any polynomial, right, the general shape of any polynomial we need to know what the degree of the polynomial is, right? So the highest power. We need to know the degree, the degree which is the highest power. So the end behavior of a polynomial will either be something like this, right? And so now we're kind of blurring out this midsection, right? And saying, hey, anything can happen in here. I guess I should have done ... to begin with there. If it's an even degree, if the degree is even, or if you have an odd degree, right? Think about, so the most basic case is x squared. As long as you know what x squared looks like, that's the general shape of any even degree. X to the power of 3, right, looks something like, or kind of like this, if the degree is odd. And then, of course, if it's negative, right, then it's flipped over the x-axis, but it has the same shape, right? So this is in general just an x squared if it's even, and x to the power of 3, which kind of goes, right, if you have an odd degree. So knowing the end behavior, even if you've got this massive polynomial, right, as long as you're able to figure out what the highest degree is, then you'll know if it's going to end up going like this. So even if you have something like, let's have a look at, let's pick a nasty polynomial here. They're all pretty tame, but what if we have something like p of x equals x to the 5 minus 9x to the 3? I don't want to draw that, right? But the end behavior, well, my degree, the degree of this polynomial is going to be 5, right? That's my highest power, which is odd. So no matter what I know is it's going to look something, and it can move around a little bit, right, depending on what it's doing, but it will look something like, now it might do something wonky inside here, right? It might go, we don't know that, but it doesn't matter because I know in the end, right, as x goes to infinity in either end, right? So here x is going to positive infinity, and this way x is going to negative infinity. I know that my y values, y is going to also negative infinity. And here, y is going to positive infinity because it's going up. Right? So this is what we call arrow notation, where we're saying, okay, as x goes to something and y goes to something else, right? We use that arrow as kind of shorthand for going to. So the next little bit, so that's all there really is about the end behavior, right? And that's all we're really gonna talk about in this section. And I know there's a whole other page, but you can do those, you can label it optional if you want, the second page of 3.2. I'll pull it back up if we need it, but what I want to do is I actually want to start 3.3 because I think we'll need more time on it next day. Okay? You'll see why in a second when you flip to 3.3. Okay? So 3.3 is on dividing polynomials. It will involve long division of polynomials, which sounds really bad. That's why I want to spend some time just kind of working through some examples. And what's really kind of odd, strange, is we're not really going to need this until Calc 2, but then you'll want it. So we'll learn it, and then you'll just remember, and when the time comes when you're in Calc 2, and they say, hey, you remember how to do long division of polynomials? You'll say, no, not really, but I remembered hearing about it. Right? And so, or maybe you'll remember because it's so fun. So I'm going to focus on long division of polynomials. On the page, right, it's got long division and synthetic division. The synthetic division is just kind of a quicker way to do it. To me, the long division just makes more sense because I'm able to kind of handle it and work through the math myself. And so I'll only use the long division. If you want to, you can read through the example of the synthetic division. It's up to you which one you use, right? But I'm picking the long division, I'm going to stick with it. So if you want to just ignore the synthetic division side, that's fine by me. Right? As long as you know one of them, then you're okay. So why would we want to divide polynomials? Well, factoring is hard, right? And so sometimes maybe I want to pull out x minus 4, for example, right? Then I want to know, just so I can cancel x minus 4 in the denominator. That happens a lot, right? And so if I want to pull out x minus 4, then I want to be able to divide it out and see what I'm left with, right? So we use dividing polynomials to help in factoring large polynomials. I prefer long division but the notes also outline synthetic division. When I was reviewing, I just kind of, I don't know, synthetic division doesn't really make a lot of sense to me. So if it makes sense to you, then that's great. So that's why I'm sticking with long division. So just some terminology, right? And this is what's on your handout, section 3.3. Oops. So if we have two polynomials, p of x and, p of x and d of x, as long as d of x is not 0, so as long as we're not dividing by 0, then there exist unique polynomials q of x and r of x, right? Where q is the quotient and r is the remainder. And so there's our terminology that we're going to be using, right? We've got the dividend and the divisor, and then it turns into the quotient and the remainder. So let's see here. How about we just start nice and slow with an example, right? Because what we're going to do, the example's there, but I'll use a different example, of course, and I'll use number 3 as our example. So number 3, if we want to have, so if we're given that p of x is 2x squared minus 5x minus 7, and d of x is x minus 2, really what I want to find is 2x squared minus 5x minus 7 over x minus 2. Now, in order to do this, what I do is I set it up just like we do with long division. And kind of a funny story. So my family, we moved around a lot. So I was born in Sweden, and then we moved to Canada, and I did half of grade 1 in Sweden, and then I went straight into grade 3 here because they start at different ages. And then we moved back. So then I did grade 3 and 4 here. Then I moved back to Sweden. So then I did grade 4 again and grade 5. And then we moved back. And so I skipped grade 6, went straight into grade 7. Grade 6 is where you learn long division. I never had to learn it until I had to teach it. What? I know, crazy, right? I don't know how I did it, but I never learned long division until I had to teach it. And then turns out it's not so bad, but anyways. So just like in long division, if you have x minus 2 that you're dividing into 2x squared minus 5x minus 7, right? We're going to set it up something like this. First note, right, is here, the 2x squared minus 5x minus 7, if there are missing values of x, right? So let's say it was 2x to the power of 3 minus 5x minus 7. What we would do is we would fill it in, so with a 0 coefficient, right? So make sure all possible terms of x are written here, right? So say we have, so say instead we have 2x to the power of 3, oops, to change that there. 2x to the power of 3 minus 5x minus 7. Then we would have to write with the x squared term as well, right? Giving it a spot. So then you would have to write 2x to the power of 3 plus 0x squared minus 5x minus 7, right? So starting from your highest power, 3, you have to make sure that you've got all the decreasing powers of x. right? 0x squared is just 0, so it's just not there. Right? In our case here, we're okay, right? We've got x squared, we've got an x, and we've got a constant, okay? So what do? I take my leading term, right, and I divide it into the first term. Okay? So what I do is, how am I going to write this and still have space? Okay, 2x squared. Well, it's in your notes, but I want to have it on here. 2x squared divided by x is going to be 2x. Right? I'll explain it down here. Divide the leading term of the dividend which in this case is 2x squared, by the leading term. This is why we had to have that terminology, right? By the leading term of the divisor, which in this case is x. Okay. So now I'm at x minus 2 divided into 2x squared minus 5x minus 7. Up here, I've got 2x. Now what I'm going to do is I'm going to multiply 2x by the x minus 2 and put it down here, down here, and then subtract it. So now I'm going to multiply and then subtract down here. So what that looks like is I've got x minus 2, just kind of rewriting 2x squared minus 5x minus 7. 2x times x minus 2 puts me at 2x squared, which it should, right? Because 2x was what I got after dividing 2x squared by x. So I get 2x squared minus 2x times 2, so 4x. And then I'm subtracting. I'm only subtracting that 4x, right? That negative 7 just gets brought down, or just stays. So now I've got 2x squared minus 2x squared, so that goes away, right? I've handled that. Now, remembering that we're subtracting negative 5x minus negative 4x, that's negative 5x plus 4x, so that puts me at negative 1x, or just x if you want, minus x. And so now, whether you want to bring that negative 7 down and just have it nice and clean there, that's fine. Because this one just gets brought down here. So now I do the same thing over again. So now I'm at negative x. And I'm not gonna keep that 1 there because it gets a little messy. So now I've got negative x divided by x puts me at negative 1. So up here, I've got -1. Because this came from, or actually this whole thing came from -x divided by x is -1. And now I do the same thing, right? So now I bring that -1 times x minus 2 and subtract it. So now I've got -x plus, so -1 times -2 plus 2. But I'm subtracting. So I've got -x minus -x. So -x plus x puts me at 0. And then -7 minus 2 puts me at -9. All right. So this, in terms of our terminology that we've got in that box, right? Because now I can't divide 9 by x anymore. So as soon as you run out of x's to divide by, right, you're going to stop once you hit the highest power of x in the divisor. And so what we have, so q of x is 2x minus 1, and r of x is -9. The question wanted us to rewrite, so therefore p of x over q of x equals q of x plus r of x over d of x. Ha, I messed up. It's p of x over d of x. That was briefly confusing to me. P of x over d of x, that makes more sense. Because the remainder, right, that -9, it's still going to be divided by x minus 2. So in our case, right, we had, what was it? Where is it? We had 2x squared minus 5x minus 7 over x minus 2. We can rewrite that as 2x minus 1 plus the remainder -9 over the divisor, which was x minus 2. So if you desperately had to pull out an x minus 2 and you don't see a way of doing it, then you can definitely use long division. You'll be left with -9 over x minus 2, but at least, right, you'll be able to cancel out because you've pulled out that x minus 2. Okay. Well, time flies when you're having fun. Yikes. So what I want you to do is just flip through the notes for next day, maybe practice some of these long division of polynomials because it's kind of tricky. And then we'll use the remainder and factor theorems. And then I just want to show you in 3.6, the last page, what I did, because I couldn't find any questions that were exactly like it in the textbook. So what I did was I just copied the page in the final exam, smushed it together. And so that is the different looking stuff is from the final exam. And then we're gonna do those problems with the functions that are on the bottom there. Okay? And so that's how we'll prepare for the final exam and also test 2, obviously, right? So have a look at those for Friday. But anyways, any questions? see you guys next day.